Presentation will be on solving queries for Boolean fault-free logic via quantified set or satisfiability solving. And the speaker will be Stefano Nicoletti from the University of Twente and Radboud University in Nijmegen.
Yeah, thank you very much. As we said, we basically are trying to solve queries for a logic for fault trees via quantified SAT. This is joint work with one student of mine, Saaltink, and colleagues and supervisors such as Matthias, Volk, Moritz, Hahn, and Mariëlle Stoelinga. And I guess I don't have to sell you fault trees because Mario has done the heavy lifting for me. I'll just put the ingredients on the table that I am using. There are numerous variants of fault trees. We consider fault trees as DAGs, right? So they can have shared children. The name is a bit unfortunate. You know, they can be also not trees, not tree-like structure. We call the objective of the failure assessment, in this case, you know, the trivial tree for a PC, at the top level event. And we call what is in between intermediate events, and then we usually refine them through gates. And here we are focusing on static fault trees, which have OR gates, N gates, and K out of N gates. So the failure to be propagated, at least K children out of N must fail. But you can see the K out of N naively as a sort of composition between N's and ORs. But those are the main ingredients that we are focusing on for this presentation. You can perform quantitative analysis, as we saw in the previous presentation, but you can also perform qualitative analysis, which is quite useful because this points out root causes and critical path in the system that you have at hand. And there is a construct that it's usually present in fault tree analysis, which are minimal cut sets, which are basically minimal sets of leaves, such that if they fail, then they cause together the system failure. In this case, you know, just the RAM propagates the failure to the top level event, or just power plus UPS because they activate the AND gate and consequently the OR gate. Fault trees are great. We have seen that with Mario, of course. They are heavily used. They are required by the Federal Aviation Administration. They are heavily used in the nuclear domain, NASA. There is tool support by isographs, among others, and they are a viable way to perform safety risk assessments on a system. However, when you usually do fault tree analysis, analysis questions are not as flexible as we would want them to be. For example, when you have what-if scenarios in mind, usually you have to retouch the model. And then we also conducted interviews with the domain experts in the nuclear domain, and they expressed this kind of desire for more flexible querying on fault trees and more complex querying on fault trees. We would like something like that, right? So we can ask questions conditioned by certain assumptions. For example, what are the minimal cut sets of a given tree, assuming that you know, a certain leaf or a certain subsystem has already failed, or that a certain subsystem is remaining operational because we guarantee it in some other ways. We can ask if the failures of one or more elements are always leading to the failure of the top level event. Or, you know, would element E always fail if at most or at least some component were to fail, right? So this gives sort of more granularity to what we can actually do in qualitative analysis with respect to fault trees. And in previous work, we did exactly that. We developed a logic, a Boolean logic for fault trees, to enable this construction of such queries. And in there, we provide model checking algorithms to check properties defined in the logic. And we provide model checking algorithms based on the binary decision diagrams. And we also provide a way to construct counterexamples, and this is also kind of a nice selling point for our work, is that, you know, when something is not how the assessor expected it to be, we can restitute examples graphically on the tree, you know, showing path or showing, hey, look, you need to add these other elements for the failure to propagate as you would have intended it. And In this paper that we present here, we present actually the first tool support for the analysis of BFL queries. And we wanted to explore a complementary approach based on SAT solving. So what we do is we introduce a translation from a BFL formula to a quantified Boolean formula. And we employ Z3 as our solver of choice. We implement this approach in Python and provide a publicly available artifact. I'll talk briefly about that as well. And then we evaluate our approach on multiple benchmark fault trees. We do have a fault tree in the original paper, which serves as our case study. But we also use a lot more benchmark fault trees from reliability engineering and from railway industry to evaluate the scalability of our artifact. And this is kind of a quick roadmap of what we are going to see, quite literally. We see some queries on the example case study that we have in the previous paper. Just to give you an example of natural language query, BFL query. This is still not quite formal, just to give you an impression of what we can ask. Then I'm going to briefly sketch out syntax and give you an idea of the semantics and the queries that we can do in BFL. I'll pitch you this translation from BFL to quantified Boolean formulae. Why do we need it? And then I'll just comment on implementation and some experimental results. So first of all, let's take a look at some colorful pictures. The original paper was in COVID time, so we thought to apply fault tree analysis to a COVID case study. So the top-level event represents an infected worker joining on site, and believe me, we did get criticism for choosing COVID because this is not a medicine paper, but here we are. Basically, this fault tree represents ways in which an infected worker can join your workplace. On the blue subtree that you see in the middle, you see modes of transmissions that are detailed. In the orange subtree, you see is there a susceptible host that is actually that could be infected with COVID, and then in the purple subtree, you see is there actually COVID on the workplace? Are there pathogens or infected surfaces or the like? So one might want to ask questions such as, is an object disinfection error always sufficient for the occurrence of the top-level event? You see on the bottom the BFL formula. Or is an infected surface always sufficient for the transmission of COVID, right? So oftentimes when you do a reliability analysis, you focus on only the top-level event. Here we can also focus on different subtrees, give more granularity. Are at least 2 human errors always sufficient for the occurrence of the top-level event? We have this kind of voting construct also for formulae, basically saying, at least 2 out of these formulae have to be satisfied. And then we can, of course, combine it with the usual Booleans and with quantification. We can also return all the minimal cut set to the user. We use the square bracket for the satisfaction set. So what are all the minimal cut set for the top-level event filtered by some kind of event happening, for example, that include the action of non-respecting the outbreak procedures. And then we can also make sure that something exists, of course, so are an infected worker joining the team and a detection error, a minimal cut set for our top-level event. And yeah, this is sort of the expressive power that we are chasing here, that we are going for when we analyze our fault trees. And I'll just present briefly syntax and an idea of semantics. This is the logic. It's tailored on 2 layers. The atomic formulae for BFL are these E, which represent elements in the fault tree, both leaves or intermediate elements. You can, of course, join formulae with the usual Booleans. And then we have constructs such as this one and this one, which we call setting evidence, which is what I was referring basically before. You want to set a certain atom in a formula to a specific value, assuming that something stays operational or that it stays failed. Then we also have an operator to check whether a given assignment on the leaves, so on the status of the leaves being failed or not, is a minimal cut set for a given formula. And then, of course, in the second layer, we can quantify, and then we can check for independence of two elements in the tree, so to speak, with the idea that two elements are independent when they have not influencing children that influence both the truth value of these two elements. And then the semantics is, you can probably imagine it. I mean, if you take a look at the fault tree, it's already kind of a Boolean function. There is in the fault tree literature this structure function, which is exactly what it sounds like. So you are given an assignment, a Boolean assignment on the status of the leaves and an element in the tree, and then basically this function tells you, yes, this element is reached with this assignment on the leaves. No, it isn't. And you can see a really quick example on the trivial model that we had before. Of course, the assignment 1, 0, 0 is sufficient to reach the top level event, so our atomic formula is satisfied. Picture this, and then we basically extend this sort of idea for all the other constructs that we have in the syntax. I'm not going to bother you with full semantics. We do distinguish between different queries. That also trickles down to the implementation of the artifact. We have query type 1, so we give a Boolean assignment on the leaves and the model, and we ask usual model checking problem, hey, is the formula layer 1 satisfied with this assignment and with this model? Query type 2 is formulae on the second layer, so we have only the tree, and then we basically ask whether there is such an assignment such that the formula is satisfied, or for all the possible assignments on the leaf, is that formula satisfied? We call it query type 2. And then query type 3 is a satisfaction set for formulae of layer 1, translated in fault tree terms, sets of satisfying assignments on the leaves such that the formula is satisfied. And I'll briefly pitch you the idea on translating BFL to QBF. So there are, of course, 3 fundamental steps in this process. We only translate needed parts of the fault tree model that ends up in the formula. We then translate subsequent first layer and second layer BFL formulae. And as you can probably imagine, there is a direct comparison between what you can see in the image and what is written there. So fault trees are already kind of Boolean functions, so there's not much surprise there when you translate the fault tree to QBF. You don't actually need quantifiers. Of course, you can have at least and at most defined in terms of ands and ors, but since we rely on Z3 at the end, there is better support there in the artifact to handle these kind of functions. The idea behind translating layer 1 and layer 2 BFL to QBF is that we need quantifiers due to the semantics of some operators in BFL. I mean, second layer, you can imagine yourself, right? You saw quantifiers. But for example, also for minimal cut set, we do need existential quantifier because we want to guarantee that there is not such an assignment, which is a subset of an assignment that we already give, that satisfies still the formula. So we have also a quantification hidden in some operator there. And then, of course, we define a recursive translation that preserves the meaning that we originally intended in the semantics of the original logic for both layer formulae. If you're curious about symbols, mathematics, proofs, you can find those in the paper. I'm just giving you the rough idea here. Yeah, and then I'll finish by talking briefly about the implementation and the experiments. Here you can go to the Zenodo repository to take a look at our artifact. Documentation is there. The basics are that the artifact again is implemented in Python, uses the Z3 solver as a backend for the solving. The entry point is our run BFL Python file. Simply takes a .bfl file as an input, where you basically specify the fault tree that you have at hand with the Galileo textual format, which is one of the industry standards for specifying fault trees in textual format, plus some BFL properties. In the docs we have instructions on how to specify properties in the BFL kind of format, but we have a parser for basically what you saw in the text specifying properties. It's all pretty simple, and we do check our experiments and our properties for the original fault tree that we have. I showed you some of these properties. Maybe you will recognize them in the first slides in natural language. And then all of these come out as expected by conducting the analysis by hand. But also we conduct 2 more experiments to test for runtime, memory consumption, and scalability. This is quite a small fault tree, and I come from the Netherlands. We are a very fan of fault trees because that's actually what keeps our feet dry, because the storm surge barrier that protects us from storms, it's actually using fault tree analysis. So we want this to scale. So we devised the first experiment, which is the single fault tree experiment. We basically take these properties, and not only we check them, we just analyze them for time of checking and memory consumption. And you see the graphs. You see on the one on the left the time over length of the QBF, or the already translated QBF formula, and then on the right, same for memory consumption. Key takeaway: there is a suggestion of a linear correlation between length of the QBF formula and the time to check it. There is an outlier in Q3, which is sort of explainable because what we are asking here is to basically return all the cut sets that satisfy the top-level event without requiring minimality, right? So this can grow and can be computationally challenging. Also, there is a suggestion of linear increase in memory consumptions. Admittedly, we have not many data points, so this can be explored further. We also devise a multi-fault tree experiments, especially checking scalability. We have 7 fault trees from reliability benchmarks. They are usually used, so these fault trees are from real-life case study in the engineering community for railway locks, basically, and more complex. And you can see Q11 and Q12, we sort of try to specify the same property for every fault tree. The first one is taking basically the minimal cut set for the root node, filtered by some events. And then in the second one, Q12, we ask, is there an assignment such that top-level event fails and some leaves have a set value? And I mean, as you can probably imagine, already taking a look at the graph, the type of property that one specifies has a great impact on runtime and memory. You see that for the time of Q11 and the memory of Q11, which are the blue and the red point, those values tell a completely different story than Q12, right? Because it's Q12. It's admittedly more simple because you're just asking for one satisfying assignment, of course. And then the second finding is that the structure of the fault tree, more than anything, has more impact on the runtime and memory than the number of fault tree elements. If you take a look at, for example, the edges of the fault tree, or at the ISP, EDF, and ELF fault tree, those are the fault tree that are more intertwined, so they resemble more of a directed graph than actually a tree in the structure. And then they have more of AND gates and voting gates than the other trees where the OR gate is prevalent. So it's not so much about the number of nodes, but the structure of the fault tree itself that impacts this evaluation. So in conclusion, we just saw the first tool to support analysis of BFL queries. We tried implementation with a complementary approach other than BDDs, which is SAT solving. We have a translation from BFL to a quantified Boolean formulae because we need quantification. And then we have an implemented artifact in Python publicly available, and we saw some graphs evaluating this approach. For future work, we want to work in 3 directions. Develop an implementation based on BDD, so we don't have just a pseudocode in our paper, but we actually can, perform concrete comparison between these approaches. We want to further investigate a restricted translation, and this was suggested by one of the reviewers, thanks for the note, that only takes a fragment of BFL without quantifier. That can also be interesting to evaluate on only SAT solving. And then maybe conducting BFL user studies to gain further insights. And then, of course, when we do the comparison, we might want to use fuzzing for generating automatic fault trees and automatic properties to keep the comparison more fair and then more scalable. not me handpicking properties and then creating files by hand. That would be nice. That's all I have for you today. Thank you for listening, and please do get in touch if any of this sounds interesting to you. I'm happy to take questions.
Thanks, Stefano. I have a question about this BFL logic
Yes.
that you showed us. You had this. There. So there you said observe that an event is true or false by setting it to 0.
Yeah.
And in your examples, it seems you only do this for basic events.
Yes.
Can I do this for, I don't know, a gate somewhere in between and then figure out what basic events have to fail or could fail for that?
Now you're asking the interesting questions. So I used only BEs because there is an asterisk in which kind of intermediate events we can do this for. We can do that if the intermediate event is the root of a module in the fault tree, which is basically a self-contained subtree, right? And if none of the children are present in other formulae. In this way, we can sort of prune that subtree, and the easy way to do this, it's maybe the ugly way, but for now this is the restriction, because we basically, if those two conditions are met, we can prune the subtree and treat the intermediate events as a basic event for all intents and purposes. So yes, asterisk.
Okay, thanks.
So, maybe it's a strange question since everybody anyways uses Z3, but why Z3? Why not, CZ4, yikes, just for, or CZ5, or I guess now?
Yes, so the main commodity that we found is that, Z3 has very nice Python APIs, so we sort of did already the parsing for the BFL and the original file in Python, so this tied very nicely in the framework that we built, and also you can sort of keep some certain values fixed and let Z3 recompute a satisfying assignment starting from a certain value, which of course maps very nicely to us wanting to have a fixed BE or root of a module in a certain configuration. So.
Very nice answer. Thank you.
Thank you.
I also have a quick question. Again, you said publicly available. Under what license?
MIT.
Thanks.
I'm ready.
License guy. Yeah, because you cannot use it if there's no.
Yeah, no, MIT.
So even if it's out there,
Yeah, thanks for a very nice talk. How do you, perhaps I was missing it, are you planning to include also probability in the next, I don't know, steps of your work?
Yeah, we do already have a paper accepted at FM, which basically extends this logic with probability, discrete probabilities, mind you, not yet failure rates, but that's already out there, and or also for that we have pseudocode algorithms for sort of building up on the BDDs method that we had in the original paper mentioned here. One of the desiderata that we have in the future is, of course, also extend this and or the BDD framework implementation to probabilities and to handling probabilities as well. Yeah.
Does this extension, or does the other paper already include some sort of a notational primitive like the voting to pick out the most critical cut set or something like that?
So yeah, basically what we have in the other logic, it's a superset of this. So yeah, anything you can specify with this, you can with the new logic, the probabilistic logic, and also I don't have a slide, but in the derived operator you saw that this voting operator here, that we have and we still have in the next iteration. We just add a layer for metric computation and bounded probabilities and this sort of machinery.
Yeah, very nice. Is there a company using it, to ask a last short question?
No, not yet, but we are sort of at least trying to integrate all of this in the Storm probabilistic model checker. Matthias Volk, the third author, is one maintainer of the Storm model checker, so we are sort of trying to push that into the model checker as well. Thanks.